Jack Gaffey will introduce our
What
speaker.
about that gentleman in the red shirt back there? I didn't hear his name.
I'm Steve Bob.
It's a great pleasure to welcome Jim Gates. You can see he's the University System Regents Professor, Distinguished University Professor, John Toll Professor, etc.
They just keep putting things after.
Well, you've earned it. Jim Gates received 2 bachelor's degrees and a PhD from MIT. His doctoral thesis was the first thesis at MIT on supersymmetry. Gates currently serves on the Presidential Council of Advisors of Science and Technology, the Maryland Board of Education. He's past president of the Society of Black Physicists, a fellow of the American Physical Society. He's known for his work on supersymmetry, supergravity, string theory. He wrote a book, Superspace, the first comprehensive book on the topic of supersymmetry, and a booklet, Art della Fisica, the Arts of Physics, and has authored more than 200 scientific presentations. Today, Jim will tell us about supersymmetry.
Thank you, Jack. Let me stand. I'm going to sit during the presentation, but I want to stand during the beginning here. First of all, thank you for the opportunity to speak to the APS Mid-Atlantic Senior Physicist Group. Jack and I bump into each other almost all the time, it seems. So
You're the guy who came to all your talks and said, "You again."
That shows you how often I see Jack at talks. You again. It's a great pleasure to be here, first of all, at ACP and among fellow brother physicists. I don't see any sister physicists in the gathering.
There are some members.
Well, I would hope so. I would hope so, but I guess they heard I was speaking, so they decided that they had better not come to this particular
We haven't
presentation.
seen it for a few weeks.
But it's a great, as I said, it's a great pleasure to speak to a group of physicists. I have, like a lot of us, I first started thinking about becoming a scientist when I was around 4 years old. I was living in St. John's, Newfoundland at the time. It's a very weird story. Dad was in the U.S. Army. U.S. military used to have bases in Canada in the 50s and 60s. Often Americans these days don't recall that, but I was one of those kids on one of those Army bases. And I saw a movie about space travel. It just fired my imagination. I learned about this thing called science because that's how you got to do that kind of stuff. And so from age 4, I was always directed towards doing science. In 11th grade, I had this amazing physics teacher, a gentleman by the name of Mr. Freeman Coney. And unlike a lot of high school students these days, Mr. Coney actually had a degree in physics, which means he actually understood physics. And so, in 11th grade, I was an 11th grader in a class of all other students being seniors. And I'll never forget when I decided it wasn't all of science I wanted to do, it was physics. And it was a very simple experiment. It was a typical inclined plane showing that the distance traveled goes by the square of the time on a stopwatch. And to me, that was magic. In fact, I tell people to today, that's the only real magic I've ever seen in life. It's the fact that you have this amazing tool in mathematics, and it describes what goes on around us. That's magic, because the math is actually in here, but the stuff that we're describing is outside of our ears. And so that immediately did it for me. I knew it wasn't all science, it was physics I wanted to do. And then I went on to, as mentioned in the introduction, I went to MIT, which I had learned existed when I was 11 years old. I thought of it as, I told my parents, it's a school where they make you study math and science and what I call the good stuff. And so I decided I want to go to the place where they made you work on the good stuff. And when I was 18, I was very fortunate enough to just be at the time when MIT was actually, it's the first time they let large numbers of African American students in. It was the year 1969. And so I was just on the cusp of that change, and boy, am I glad.
Boy, you're lucky, yeah.
Yeah, boy, was I lucky. And so it opened the door for me to go on and make those childhood dreams a reality. My first degree, I have 2 degrees. The first is in mathematics. The second is in physics. And that's an accident. I went to MIT wanting to become a physicist, but my grades were better in mathematics, and I knew I wanted to get into grad school. So I declared myself a math major. And as a consequence, took all the standard sequence in mathematics, also took the standard sequence in physics, enjoyed the heck out of the physics ones, got through the mathematics one, but the grades were better. It was always very strange to me that I enjoyed the thing more, that I got the more, that it was a struggle to perform on grades. And then when I was a senior, a friend of mine said, well, what degree are you going to get? And I said, well, I'm a math major, so I'm going to get a BS in math. And she said, but I saw you taking all those physics courses. I said, yeah, I love physics. It's fun. And she said, well, I bet they'll let you have both degrees. And I thought, how? That's not right. So we went over to the physics headquarters. They looked at my transcript. They said, oh, you look just like a physics major, with one exception. You haven't done the lab courses. So they made me do the lab courses during my senior year. I also at MIT in those days, you had to do an undergraduate thesis. And so my math degree I got in June. I didn't get my physics degree until August or September because I was busy finishing the write-up in the lab courses and the undergraduate thesis. But physics has always been my love, and so I'm always happy to share it with people in whatever venue. So let's get started on today's presentation. So I gave Jack a couple of options about what we could do today, and he picked supersymmetry, which is the subject that I've spent my entire adult life as a physicist working on. So we're going to talk about this stuff, and hopefully it will not be boring for you. So this is my thesis. It's the first thesis at MIT where anybody discussed anything about supersymmetry. It was very remarkable set of circumstances from my point of view. I was in my second or third year of graduate school. I was trying to figure out how I was going to write a thesis. I did a big literature search about what was going on in the physics literature at that time. This is like 1975 or so. And out of this list, I found this new subject that had only been being pursued for about 3 years at the time. And I thought, God, how could you be so lucky to find something that's only 3 years old in theoretical physics? And I also immediately understood that it implied that there would be more forms of matter and energy than we had ever conceived of before that point. And I just thought, that's got to be the thing that I'm working on. The other thing that attracted me to it was the mathematics of supersymmetry is rather extraordinary. It's unlike most of the mathematics you learn as a physicist. It's beyond vector calculus, it's beyond differential geometry. It's really weird, but since I had this math degree, I also enjoyed weird mathematics. So it was the ideal subject for me to begin to work on for a thesis. I went to my advisor. I asked him would he be willing to let me change from some standard stuff I was doing on the weak interactions. And he said yes. But then he said, I don't know anything about that stuff. And then he stopped and said, well, actually, nobody at MIT knows anything about that stuff. So how are you going to do it? And I said, well, I'm reading the literature. And he demanded that I come once a week to give him a seminar on what I had learned that week. And so that's how I actually produced my thesis. And this is the cover from it. I defended it in 1977. One of the people on my defense committee was a guy named Ernie Moniz. He's currently our Secretary of Energy. And at the end of the thesis defense, he was very complimentary, and he said that was the best thesis defense he'd ever seen. And for a young student who, if you're a minority student and you don't see many people who look like you, to have that kind of complimentary support, I can't tell you how valuable that is. So if you have a chance to, if you have a young person that you bump into and you have a chance to give them something supportive like that, it makes an incredible difference. And so I will always treasure that remark from Ernie when I defended my PhD thesis. Some of you know I did this. In fact, we talked about this. I only show you this because a number of the graphics in my presentation come from this. And they have rights to a lot of this stuff, and so the agreement is that I acknowledge that the graphics have this as a source. So this is my bucket list. And in fact, it's funny because that DVD series, which one of your colleagues complimented me on this morning, at the time that I wrote it, it was supposed to be on string theory, but I decided to take it as a license to talk about theoretical physics, because that's really my love. And so this is 2006. I thought within about a 10-year time span, what are the things that I would love to see happen? Well, the discovery of the Higgs boson hadn't happened in 2006. So that was part of my bucket list, and you'll find it discussed in the series. Gravitational waves hadn't occurred at that point. I had been watching the progress of LIGO since around 1987. Rick Erickson, who was an alum of Maryland, but was then a program officer at the NSF, first introduced me to LIGO. And so I had been on one of its advisory committees. I'd been watching progress of the project. I knew Ray Weiss and Kip Thorne. And so to me, that was just grand physics on cosmic scale. So I said, gee, it would be great if that occurred in the next decade. And then supersymmetry. That's the thing that I do, and so of course I was hoping that we might have signs of that. And then there's this thing called superstring theory or string theory, which I've done a lot of work on in my career. And although it's on my list, I thought I would have to be incredibly lucky for this to occur. But I also have to remind you that the teaching company asked me to give a DVD series on string theories. I had to include on this list anyway. So Higgs bosons we discovered in 2013 with the announcement that came out on July the 4th. I like to say the Higgs boson was born on the 4th of July. To me, that's a very incidental thing that I love, the fact that the universe worked that out that way. Then the gravitational waves in February of this year. It was just amazing to actually see the evidence of gravity waves come out. And come out in a way that we didn't expect, because those of us who had been following the project for a long time, our expectation was that the first gravitational waves that we would hear would actually be from binary pulsars or binary stars, which are a much more long-term event. The coalescence of black holes is something that happens sort of after a while. It's not a long-standing event. And it produces these chirps. So we thought the chirps would probably not be the first things discovered. But Mother Nature, with her wonderful bag of tricks, decided that we would hear chirps before we heard rotating neutron stars or pulsars or what have you. And so that was just an amazing day when that happened. Super partners. Well, we're going to spend some time talking about these. We haven't seen them yet. And then, as I said, superstrings, who knows? Who knows when that will happen? It'd be nice. Okay, so here's the standard model, represented in much of the same way that you can use Mendeleev's table of elements to do chemistry. This is a very standard. Oh, by the way, if anyone says, I'm talking fast, I have a lot of material to get through, please stop me, because this is not meant to be a soliloquy that I deliver to you. It's supposed to be interactive, so if you want to chime in at any point, please do. So here's the standard model with the electron here, the photon, the family of leptons, the mu, the tau, the family of quarks, up, down, charge range, top and bottom quarks. The quarks, for me, have an interesting sort of marker in my life. I was a senior in high school, and I remember reading in the Sunday paper supplement an article entitled, "Hark, Hark, Little Quark, Bev is going to find you." Now, Bev, of course, if you're a particle physicist, you know, Bev was the billion electron volt Stanford linear accelerator. And in '69, they provided, through the deep inelastic scattering experiments, the first experimental support for the idea that quarks were real objects that govern the structure of hadrons, as had been anticipated by Murray Gell-Mann when he proposed the eightfold way and these sorts of models. So here's the standard model on July the 3rd of 2013, and there's the standard model on July the 4th, because we have to add the Higgs particle, so I've denoted that addition here. The Higgs particle is an amazing construct. It's won a Nobel Prize. It was, in fact, the physics I first studied when I was a graduate student before I decided to do supersymmetry. And when I made the transition, my advisor had me studying this. And we all know how this sort of works. You have a bunch of gauge particles, which I've represented by these dots at the bottom of this image. And then you have this other object, which is called the Goldstone boson. And we physicists write potentials for these things. And it turns out that the potential that we write for the Goldstone boson is an inverted potential. So it's the opposite of the usual harmonic spring potential. And you know that as a physicist, that at the very tippy top of this is an unstable fixed point. And if there are any fluctuations about the fixed point, then of course, roll down this unstable energy surface until you find a minimum energy. And so the Higgs model, which actually describes this process of mathematics, is relatively straightforward, basically tells us that that when the Goldstone boson reaches this minimum, what happens is the W particle and the Z particles gain mass while the photon remains massless. And so that's actually the Higgs model. Of course, the Higgs model doesn't just do to Peter Higgs. And many of us who follow that story know that there's a whole ensemble of physicists who contributed to that. Braut, Geralnik, Kibble, Engler, and even Tuff. So And of course, Angler shared the Nobel Prize for this work.
They can only give it to 3.
You can only give it to 3, but it's about a group between 5 or 7 physicists who actually made that discovery possible. And of course, the discovery occurred in CERN, at the Large Hadron Collider. I don't have to remind this group that we in the United States in the 90s wanted to build something called the Superconducting Super Collider, and our Congress came back and told us no. It was a source of great disappointment, but it also then set some directions for future history. So when we dropped the ball, the Europeans in CERN facility picked it up. They repurposed their old LEP, LEP accelerator, upgrading it so that it became the Large Hadron Collider, repurposing the tunnels and adding new superconducting magnets so that you could force the high energy particles in circular paths. And so the discovery was made there. I have to tell you a story about President Clinton and this. So in 1998, I was in the White House for the first time, and there Stephen Hawking was speaking. And there was a reception line afterwards for, in one corner there was President Clinton, in another corner there was Stephen Hawking, and in the third corner of the room there was Mrs. Clinton, First Lady Clinton. And so my wife and I were at the reception. We met President Clinton, and so he looked at me. I had, during the presentation, Stephen Hawking had mentioned supersymmetry. As you know, it's kind of difficult for Stephen to handle a Q&A session, and so they had salted some physicists in the audiences to respond to the questions that came up after Stephen's recorded lecture was finished. And so I was invited in that capacity to the east wing of the White House. And as I said, afterwards we went up to President Clinton. He had observed that I was one of the people responding to questions. And so he said to me 3 things. He said, let's see. The first thing he said was, we didn't realize that when we moved Lloyd Benson in my administration, it meant that the support for the for the SSC would not occur in the United States. Now, another friend of mine is a guy by the name of John Toll, and John had a different story. So I think I probably trusted John's story a little bit more than the story I heard from the president. So that was item number 1. And then the second item, he said, but we'd be very happy to know that the technology, in particular superconducting magnets that had been proposed to be used in the collider in Texas, we've made a commitment of $500 million, including that technology, to the Europeans so that particle physics will continue to have an option to make advances in the United States. So I thought that was great. And then the final thing he said to me, which I found very humorous, is he said, and we also saved minority set-asides on the highway bill today. And I thought, interesting. Physics, black. I wonder why he did that. So here's a cartoon of the LHC. And as we all know, it's a tunnel under the ground near to the Alps, approximately between 150 and 300 feet underground. But it's not that the device tilts, the ground's tilting because it's going up to the base of the Alps. And you can go down in tunnels to the various beam detectors. The CMS, compact muon solenoid, is one of the detectors that came out of that commitment that President Clinton was speaking to me that night in 1998. The Atlas detector is another one of those commitments. But there are other experiments at LHC that don't get as much attention. I'm going to return in particular to LHC-B, which is an experiment that's underway there. But I won't be talking about Atlas. Atlas detector this is a cartoon. It's basically a hadron calorimetry device. We measure the deposition of energy as particles fly out from the interaction region with a very marvelous technology. The amount of data that these devices takes is incredible. It's terabytes of data and it's stored and processed. And in fact, some of the processing of the images I guess the Atlas has its own theme. So there we go. Yes, indeed. And so this is an incredible device. It actually does some of the processing of the information actually in the device before it reads out to computers. silicon vertex technology is used in the detectors. And I don't know if any of you folks are detector folks, but this is just an incredible device. When I talk to the public, I say this is the world's greatest iPhone because it takes pictures. And then, of course, it has the corresponding device, the compact muon solenoid. And again, just amazing technology. It's the kind of technology when you're a physicist, if you ever get a chance to visit this place, you kind of walk in and you look at them and you think, yeah, this is why we do physics. Because no other group of people in the world are capable of doing this kind of stuff. And it's certainly true. It's very impressive technology. The actual LHC consists of basically an evacuated pipe where we run beams of protons clockwise and counterclockwise, separated by some distance. We use magnets to bend them, and then in the interaction regions, we allow them to collide. And that's where we do our observing at the CMS as well as the Atlas detectors. These are detectors that are principally funded by Americans. They each have about 3,000 physicists working on them, although there are international physicists, but it's a consortium of physicists from around this country that work at the devices. And so the actual discovery of the Higgs particle, although it happened in Europe, it would not have happened without American know-how, American technology, and American personpower. So we, in fact, enabled the discovery of the Higgs particle. And this is a picture of the Feynman graph of the processes involved. Basically, you take protons, you collide them. Protons, of course, are inside of hadronic matter. There are also gluons inside of hadronic matter. The gluons can interact in such a way to produce a process called gluon fusion. When you get gluon fusion, gluons are not stable particles, they can decay. And one of the decay modes that gluons undergo is in a Feynman graph involves a loop of quarks in this characteristic shape. And we're going to come back to this shape because it's the kind of Feynman graph that occurs when one is trying to find anomalies. However, the vertex here is actually where the Higgs boson is produced. So that's how we produce Higgs bosons. Collide the protons, get the gluon clouds around the protons to interact, and then interact in such a way that one of their decay modes is the Higgs boson. So that's how we produce them. And then the Higgs boson, of course, itself is not a stable particle. So it decays into another one of these triangle diagrams, but this time we look for decays into particles, into gamma particles at the vertices. And so what the detectors do is actually look for these gamma particles. And then there are another corresponding process where leptons come out. In particular, electrons and their antiparticles, and that's what we illustrate here, or muons and their antiparticles or tau particles. So these detectors are optimized to detect these decay channels of the Higgs boson. And there's lots of data. The machine is running incredibly efficiently. This is as of 2011. These are plots of the amount of data taken in. This is a plot of the machine's efficiency. So its luminosity, which is the brightness of the beam, and then you can see it ramped up until about the 1st of November. So that's what enabled the discovery of the Higgs boson. So as I said, it was born on the 4th of July. That's when the announcement came out to the world. There were slightly different masses measured by the two different American-enabled detectors, both around 126 or so. And at that time, it didn't make the standard of a 6 sigma deviation, but it was 5 sigma when you combine the data. So we were pretty confident that indeed the Higgs boson had been found after being searched for 40 years. This is a copy of the announcement that came out. That's a picture of Ralph Heuer, who was the director of CERN at the time. And I highlight in red something of that first announcement because, to me, they were doing some very interesting things in the wording of this announcement. And as any of you know who have worked for physics facilities that interact with the public, there's a whole science about how you write about what's being done. You don't just get a group of us in a room and we put some sentences together. There are real pros at this business of when you interact with the public, because you have to be at the level that ultimately you're dealing with politicians, so you've got to really be at the highest levels in communication at that point. So there was this very funny thing that was in this first announcement, and I've highlighted it in red. It said, or possibly the lightest of several bosons. Now, for most people, this went under the radar, but I immediately at that point said, uh-oh, what are they hiding under? You know, it's like the guy behind the curtain. Oh, I'm sorry about this. Let's see, get rid of that. There we go. What were they hiding on the curtain? I thought that there was a greater story that they were going to tell us or that they were hinting at. So, that's real physics. This is also real physics. I'm now going to take you to the realm of science fiction. The way that we're going to do this is to go back to the thing that fascinated me when I was a grad student. This is another representation of the particles in the Standard Model. In this quadrant here, we have all the matter particles. So the electron, the muon, the tau particles, their associated neutrinos, and we've broken the particles into their left. Well, one way to think about it is helicity positive and helicity negative states. That's how we've broken this up. We've done the same for the quarks here. And then in this upper quadrant, we have the force carriers. There are 8 gluons, which are the carriers for the strong nuclear force. There's the photon, they carry the electromagnetic force. Jack was telling us that there was a wonderful documentary. I hope they use the word photon in that documentary. I don't know if they did because I don't watch TV.
I haven't, well, to see, I haven't.
Okay. And then there are the carriers of the weak nuclear force, the Z particle and the W boson. And then, of course, we added the Higgs. So this is a representation of the Standard Model, where what I have done here is I've plotted whether the Standard Model particle is a boson, like a particle of light, or a fermion. All fermions obey the Pauli exclusion principle. No boson obeys the Pauli exclusion principle. So that's what distinguishes these two classes of objects. And then the other part of my demarcation is I've just noted what plays the role of force carrier, and I just used the nomenclature energy, but I'm really talking about particles that carry forces along this row, and then the matter particles are the particles that are subject to the forces. So this is what the Standard Model looks like if you decide to represent it along these two axes. And you can easily look at this diagram and say, you know, that's not very symmetrical. And yet, the principle of symmetry has been one of the most powerful tools we physicists have been exploiting all the way back to the time of Newton in some sense. In The Elegant Universe, Steven Weinberg has this wonderful quote where he talks about the fact that Newton unified the celestial with the terrestrial. And that's right, because he's talking about gravity as it acts on Earth with the falling apple versus the effects of gravity keeping the planets in their orbits. So there is indeed a unification there. And so this idea of unification is a tool that we physicists have been using, and the mathematical realization that it often relies on is symmetry. So again, I refer you to this diagram, and you notice that it's highly asymmetrical. This is a thing that I was sensitive to as a graduate student in 1975. I had studied the physics of elementary particles, and I was aware of this asymmetry. And although most people didn't think very much about it, and about 3 years earlier, there was some mathematics that started being developed. And first, actually, even earlier, in the Ukraine around 1967 or 68, two physicists by the name of Goffman and Lichtman were the first people to write down equations that had the property of supersymmetry. But in those days, there was this thing called the Iron Curtain, so we in the West knew nothing about this work. Shortly, about 3 or 4 years after their initial proposal of this idea, there were people even then studying the first generation of string theory. And in string theory, it turns out that if you studied at that time, and if you study the modes, the vibratory modes of the string, you could create a model where you could show that some vibratory modes that had the properties of fermions, and therefore obeyed the Pauli exclusion principle, and other vibratory modes that had the properties of bosons could be interchanged in the mathematics of strings. So this is how we in the West came upon the idea of supersymmetry. It was by the study of strings where you look at the properties of the two different classes of vibratory modes of the string, and you notice there's a mathematical way to transform between these two sets of oscillatory modes. And so this inspired Julius Vess and Bruno Zumino in order to write a set of equations that allowed this transformation that was discovered in string theory, but in the context of ordinary quantum field theory of the type that we use to describe the standard model. And so that's how supersymmetry got its Western birth, was from that axis. But it's exactly the same mathematical idea. And once you get the idea that bosons and fermions mathematically can be interchanged, then you can ask, is there something we could do to make this table more symmetrical? And the answer turns out to be yes. You can add particles. Now, if we live in a universe that is, and as you can see, this diagram has a left-right symmetry. Now, you might ask for an up-down symmetry to be added, but if you did that, you would be talking about more than 4 forces. This is the maximum symmetry you can have if there are only 4 forces in nature, not more than 4 forces. So no, it doesn't have an up-down symmetry, but it does now have a left-right symmetry. And one of the peculiar things to note is that here's the Higgs boson on this part of the diagram once more, but if you want a supersymmetrical universe, you actually have to add 4 more Higgs bosons. And that's why that announcement that came out of CERN to me really had me perking up my ears, because I knew that in the context of supersymmetry, there would not just be 1 Higgs particle, there would be a total of 5 of them. And so I was wondering were they actually seeing signs of more than 1 Higgs boson, and that's why I highlighted that red particle. That red portion of the announcement from CERN. So how does it work? Well, supersymmetry, and that's all we're using the S for here. Supersymmetry basically says that every particle, and when I say particle, I'm a field theorist, so I mean particles and fields for me are interchangeable concepts. So there's a field that describes a particular class of particles. So what supersymmetry says is for every particle, so let's take the graviton, which is a spin 2 particle. Supersymmetry says there's an associated force carrier that is a fermion. Spin 2 is a boson, doesn't obey Pauli exclusion. It has to have an associated force carrier that does. And we call this thing the gravitina. In a similar manner, the W particle, well, let me do the gluons first. The gluons, there are 8 of them, responsible for the strong nuclear force, the exchange of quarks in the interior of nuclear matter. There have to be 8 gluinos with this idea of supersymmetry. The photon has to have a superpartner called a photino. The Z particle has to have a superpartner called the xenon. Now, none of these superpartners have ever been seen in our experiments, but mathematically, they're the things that cause this table to have the symmetry. So that's why partly we're looking for these things. Now, my favorite superpartner, and I've told this joke many times, but I'll tell this group also. My favorite superpartner is actually the superpartner to the W particle. There are 2 W's, a positive and negative charge W, and so there will be 2 spin 1/2 particles that are the superpartners, whose name is spelled W-I-N-O. On many occasions, I've made the observation that I would love to live long enough to one day see a headline, W-I-N-O seen in Geneva.
Yeah.
Because most people looking at that headline, their first response will be, who cares about an alcoholic, right? Whereas for physicists, we will know that it's the superpartner to the W particle that would have been seen. Same thing for quarks. So in our universe, we have up and down quarks. If they are these superpartners, which are, the quarks are particles that obey the Pauli exclusion principle. The quarks do not obey the Pauli exclusion principle. They're spin 0 particles. If I go back to our table, the quarks are over here. They're fermions. They're in the fermion column. The squarks are over here. They're in the boson column. These would be bosons that carry color, just like quarks carry color. And therefore, yes, sir?
Yeah, you say color, but you seem to have left out color in these charts.
Yes, that's true.
And the strange thing is that the color is one of the things that's stable about these particles.
That's true.
Whether it's one or the other of these classes.
Sure. So the reason I left out color was for simplicity. If you want to include color, what that entails is taking this box and taking this box and then writing 2 more copies of them, because those are the other 2 colors. I didn't represent all 3 colors in this diagram. As I said, just for simplicity.
Well, there's more than 3 colors.
No, there are only 3 colors. SU3. That's why it's called SU3. There are only 3 colors.
There's a higher symmetry.
Say again.
There is a higher symmetry.
It's if you want to think about it, it's
White is a color, and then there's 4 more colors beyond that.
white is not a color. White is a combination of colors. There are 3 colors. That's why there are 8 gluons, because it comes from the SU3 symmetry.
That's a matter of definitions.
No, it's a matter of observations. Jets of these things have been seen in experiments, so we know there are 3 colors. There are other reasons for why. There's a very famous decay, by the way, which is pi go to gamma 0. That decay is also sensitive to the number of colors that quarks carry. So we know there are 3 colors from observational experiments.
Are there supersymmetry gluons?
Yes. Those are the gluinos that I. Okay, so here are the gluons. This little ball here represents all 8 gluons. Here are the gluinos, the supersymmetric partners to them. Okay. And of course, it happens for neutrinos. So there's neutrinos and sneutrinos. So the electrical variety, the muon variety, and the tau variety. And then, of course, the electron has a superpartner. We call that the selectron. The muon has a superpartner called the smuon. The tau particle has a superpartner called the stau. So this is again
not all been observed.
None of the superpartners have been observed. Or as there's a famous joke about this, that we know supersymmetry is right because we've seen half of the particles. And of course, people are talking about this half. Right?
Yeah.
So this is a joke that's been around in my community for years and years. And we know it's right, that's because we've seen half the particles.
Half right.
Half right. So now remember, we're really also incorporating the principles of relativity and quantum mechanics in this discussion. And in particular, I don't have to remind you that our community birthed several revolutions in the view that humanity has of the universe in which we live. Going back to Bohr's observation of Bohr quantization, begins to tell us that Newton didn't get it all right, because you can describe the dynamics of an atom, you take Newton's law, then you put this extra condition in. That's not a paradigm. And so as soon as Bohr made that observation, which was generalized by Wilson and Sommerfeld, a crisis developed in physics. You can't just take physics off and throw in something extra and claim you understand the system. You actually have to have a complete paradigm in order to understand where these extra things came from. And that, for us, occurred with Schrodinger or Heisenberg around 1925 or 26, when Schrodinger wrote his equation. Heisenberg created matrix mechanics, and shortly thereafter it was realized the two of them were the same. So that's when we really understood quantum mechanics.
You should correct the spelling of Roland. It's G.
Ooh, you're right.
Yeah.
Thank you.
Rosier.
Yeah, thank you. Of course you're right. Now, this difference on bosons and fermions is really rather interesting. And the simplest way that one can understand this difference doesn't involve going all the way to relativistic particle physics. You can see this difference if you're teaching a physics class, like I have to do from time to time, by pointing out the following to students. So in quantum mechanics, one of the first systems we all study is the so-called particle in a box. We have a free particle, we have infinite walls that is bouncing in between, and then we look at the behavior of the solutions to the Schrodinger equation in this environment. So this is something I just pulled down from Wikipedia. Here we have a particle in a box. The wave function has a set of states. So here's the ground state solution. Here's the first excited state. Here's the second, third, fourth, and fifth. So this is all sort of third, fourth year undergraduate physics that we're talking about here. Now, one of the interesting things that interesting variation on this that you can teach students very early, it's about 2 particles in a box. 2 non-interacting particles. That is, 2 particles that only interact with the walls, but not with each other. And then ask the students to solve the Schrodinger equation for the 2-particle system. Now, if you do that, you can calculate the energy levels associated with the system. And those energy levels, not surprisingly, are the sum of the energy levels for each of the 1 particle in a box system. And now, the beauty of teaching students about what's the difference between a boson and a fermion occurs. If you have two identical particles in a box and they are bosons, you can then ask the question, what does indistinguishability impose on the presence of the description of the particles? And what does that mean for the energy levels? And in particular, for two identical bosons in a box, the lowest energy levels are when the occupations each take the value of 1. So therefore, the energy that you measure for the two-particle system is actually twice the energy of a one-particle system. Now, put two identical fermions, and I notice I've also have a spelling error here. Now put two identical fermions in the box. And once again, fermions have to obey the Pauli exclusion principle. And what that does when you look at the ground state is that it says that both of these occupation numbers cannot be the same number. One of them has to differ from the other. They both have to be non-zero integers. And so either the occupation of the first electron particle is 1 and the second is 2, or the occupation of the first particle is 2 and the second is 1. And therefore the energy, the ground state energy of two identical fermion particles in a box is 3 times the ground state energy of the single particle wave function, not 2. And so even at this very simple level of quantum mechanics, you can understand the difference of what a distinction a boson and a fermion makes at a quantum mechanical level. You don't have to go all the way to quantum physics to begin to discuss this. So, Susie, well, so 1977, I wrote this thesis at MIT. Back in those days, the number of physicists studying supersymmetry was incredibly small. In fact, we were kind of disreputable. Really, the people who were doing real physics were studying things like dilute gas approximation or instanton physics or various aspects of QCZ. And so we were left alone in the corner and said, oh, you know, just how you have a wayward child, but as long as it doesn't bother anyone else, you just let it stay in its corner. There were a group of us in the world in those days, and that's how we were treated, but that was just fine with us because there's an aspect of supersymmetry that I'll come to at the end of this talk, which is rather startling, which is why I think many of us studied in those old days. That changed in 1980. In 1980, it was realized by several different groups. One of them was Arnowit Nath and Chamsadine in the early 80s, and then a group involving Peter Nellis and I'm sorry, I'm blanking on other physicists at CERN. Both pointed out that the mathematics of the Higgs mechanism, which is applied in weak reaction phenomenology, also can be applied to supersymmetry. And that if you apply that sort of mathematics in the context of supersymmetry, the reason you don't see the superpartners in all the physics we've known is because the rest of these objects have masses. Because it's the Higgs is basically the analog of the Higgs mechanism, splitting the mass spectrum. But now it's not that you're splitting the mass spectrum only among force carriers. You can also look at the mathematics, and that's what these gentlemen show, and show that the objects that are missing in this table can all be extraordinarily heavy compared to the masses of the particles that we observe in the Standard Model. And it was at that point, around 1984, when large numbers of physicists decided that supersymmetry was very interesting to study. And so, around 2007 or 8, the Large Hadron Collider turned on. There have been many, many searches for these superpartners. I remind you that when the Large Hadron Collider initiated its operation, it was operating at a center of mass energy of about 7 TeV, which I always like to remind people that the SSC, had it been built, was designed initially to operate at a center of mass energy of 21 TeV. So the SSC was, at initial operation, was 3 times the initial operation of the LHC. Now you need this energy because if the particles are massive, you got to go have the energy available to excite those states. And that's why the capacity of a machine in its energy range is a very incredible question to look at. Now, when the LHC turned on, there were many people who said, "Oh, we're going to find these super partners almost as soon as the LHC turns on," and because of that, there were lots and lots of experiments. And each one of these lines that I'm showing you in this chart, each one of them is a separate experiment that was undertaken at the LHC to look for the evidence of super partners. In its initial scientific run, 2007, 2008. So they were looking for particular decay modes. Those are described here. These are some of the names of the models that were being explored. But it doesn't end there. I'm sorry, this one, these were Atlas SUSY searches that I'm showing you here. These are CMF SUSY searches. So large numbers of searches have been done looking for these particles. And guess what? We haven't seen a thing. There's been zero observational evidence that super partners are out there. But if you understand what's been going on, there's a funny thing at work here. The searches that have been undertaken at the LHC are almost all within the context of a set of assumptions. Because it turns out that when you go from that small list of observed particles to the balance table, there are lots and lots of new parameters that enter your Lagrangians. In fact, there's about 100. And so, in order to make predictions, it's exploring a 100-dimensional parameter space is not going to be easy. Anyone who's done any kind of searches know that. So one of the things you can do is say, well, maybe nature will be kind to us. Maybe I can figure out an argument to constrain some of those parameters. And so, in fact, most of the searches that you have heard about looking for supersymmetry have been in the context of something called the constrained minimal supersymmetric standard model. And what they do is of those 100 parameters, they leave only 5 of them to vary. And so, if you follow the discussion in the media, at the end of the first scientific, or near to the end of the first scientific run at the LHC, you can find stories in newspapers, "Oh, supersymmetry is dead." And there are physicists even who, at least some, who say, "Oh, well, we don't have to worry about that one anymore." But the only problem with that is that some of us know what's going on behind the curtain. And so, rather than saying supersymmetry is dead, I would claim something else is going on. First of all, that statement's wrong. It's not, from my perspective, it's not good science to say, if I have a 100 parameter space to study, and I make some assumptions about 95 of them, and I claim I can't find the effect, that doesn't sound like good science to me. But that's what's actually happening. So, this is one of my my ways to explain to people about the search for supersymmetry. This is a variant of another joke I really like. I'll leave this one up, but I'll tell the other one. So there's a joke about a patron coming out of a bar, and he encounters a man on his hands and knees, scrambling, looking for his keys. And the patron is a good Samaritan, so he asks what's wrong, and gets down and begins to search, and he searched for half an hour, 40 minutes. He can't find anything, and so the patron finally asks the person who was initially doing search, "Well, we can't find anything here. Where did you actually drop your keys?" And so the person says, "Over there." And there are no street lights over there. And so the good Samaritan says, "So why are we searching over here?" He said, "Well, this is where the lamppost is." And that's effectively what has happened in the search for supersymmetry. The guesses have been placing the lamppost, and they've been searching under the lamppost. So, in 2006, before the LHC turned on, and while the vast majority of physicists were claiming, particle physicists were claiming supersymmetry was around the corner, I actually wrote an article where I said I didn't think that was right. It's a public article, it's published in Physics Today, we'll get to that. And so, before this recent scientific run of the LHC, I was asked by Physics World what my perspective was on the prospects of discovery now, since I got the first time right. And basically, I said, I would not be surprised if we still don't find supersymmetry, and I'll come back to that, why I have that intuition. But I did write this article called Sticking with Susie, which is available online, in which I talk about the search for Susie. To me, looks like a guy who searched on the East Coast looking for giant sequoia trees. You know how successful that search would be, because they don't grow on the East Coast. Right? You got to go to California, the West Coast. That's what's happened so far. So, as I said, in my view, the current situation is like some guy was looking for giant sequoias on the East Coast. It's not a very convincing search. So finding Susie is going to depend on looking in the right place, in my opinion. I've always felt that. And another example, as I said, is that Susie, at least in my mind, can be subtle, and the fact that there's a minimum of 5 Higgs bosons suggests that this subtlety is the way to start searching for Susie. The searches that we're talking about are what I call direct production. Namely, they're predicated on the notion that you can produce the superpartner just like you produce a Higgs and then watch its decays. That's direct production. So why would nature possess more than one Higgs? It turns out that that's something you don't need supersymmetry to understand. I like to tell that story because it's going to be related to some other important things. So if you look at the standard model, what it does is it takes the neutrinos. This is for my thesis. It takes the neutrinos that are associated with the electron, and it doesn't put them in a 2x2 matrix. There should be these are 2 different vectors I'm showing here. And so it puts the left-handed particles in one state, it puts the right-handed particles in singlet states. But if you're a particle physicist and know the mathematics of relativistic quantum field theory, there are these things called anomalies. When you have chiral asymmetries in a quantum field theory, you can produce a theory that makes no predictions at all. They're called anomalies. So it turns out that the reason the supersymmetric particle has to have 5 Higgses is because that's the number that gets rid of anomalies and allows it to make predictions. So this is to me, this is a very strong hint about what you ought to start looking for. Now anomalies, I would like to remind you, come back actually to this thing called the triangle diagram. There's a very famous story about this diagram. And so the basic idea is that you can have a force carrier, let's say something like one of the weak force carriers, that connects to a triangle. And in this triangle, you have fermion loops running around. So these might be electrons running around a loop or muon particles, of course. I don't really care what they are. But let's look at them on a chiral basis. And at these other vertices, we look at other force carriers. It turns out that this kind of diagram, if you calculate it in the context of quantum relativistic quantum field theory, if you calculate this diagram, it will induce an effect of breaking the gauge symmetries for the gauge carrying particles. And since gauge symmetries are extraordinarily important because they are what lead to local conservation laws, the breaking of a gauge symmetry is a big deal. Now, there's a story about this diagram. I don't know if it's true or not. Maybe one of you in this room will do. Yes, sir.
Does that diagram also depict neutrino oscillation? Different kinds of neutrinos?
No, it doesn't, to my knowledge. And the reason is because the external states here all spin one states, and for neutrino oscillation, you need to have external states that spin 1/2. So maybe a diagram like this could be embedded into such a diagram, but it can't do it as you suggest. Now there's a story about this diagram, and I don't know how true it is, and maybe one of you can tell me if it is. But the first person who discovered this effect, that these things can break symmetries, was a graduate student. And so, at least the way the story goes. His advisor gave him a problem to calculate in relativistic quantum field theory. It involved this particular diagram. He did the calculation one way, he got one answer. He did the calculation another way, and he got a different answer. So he looked at through calculations, tried to find the error, could never find them. Went to his advisor saying, I got these 2 different answers for these processes, and I can't figure out why I'm getting 2 different answers. Supposedly the advisor also began doing calculations and had the same thing happen. and sort of threw his hands up. And so the student had a very interesting response. He had wanted to be a theorist, but he decided to become an experimentalist. Now, I don't know if this story is true, but I remember hearing it as a graduate student. This is the power of anomalies. They can turn theoretical students into experimentalists, apparently. So these types of diagrams are very, very significant in the context of relativistic quantum field theory. And it turns out that they're so significant that they seem to control features that you would never guess about the standard model. If you look at the electrical charge of the up quark, which is plus 2/3, compare that to the charge of the down quark, which is minus 1/3. This equation obviously gets satisfied. So you have 2/3, minus 1/3, 1, that's 2/3, right? This is true for the charm and strange quark, also for the top and bottom quarks, but it's also, you can extend this equation, and this is, of course, dumb algebra that we're doing. You can say if you take twice the charge of the electron and add to it 1, and divide by a third, and multiply and subtract from 1, that's also equal to the same number. Now you might think this is numerology, but in fact, these particular equations are precisely what you need so that when you ask the question, is gauge invariance preserved on the chiral states in the weak interaction model, do you preserve gauge invariance? The answer turns out yes. These equations are why you preserve gauge invariance, so it's not just numerology. So the fact that the up and down quarks are not fractional is connected to the existence of gauge symmetry for the electromagnetic field in the standard model. It's a very subtle effect. So these anomalies, as they're called, are extraordinarily interesting, even to mathematicians, it turns out. And quantum processes that are not anomalous, well, I'm sorry, here we use the words anomalous in a different sense. I'm again sure that many of you in the room are aware of these so-called G-2 experiments, which involves measuring the magnetic dipole moment of the electron and then comparing it to predictions first measuring it, then comparing it to predictions from relatives to quantum field theory, where you include hundreds of Feynman diagrams to correct the classical value of 2. And this is this experimental versus theoretical observation agree to this many decimal places. It's an incredible agreement. It's Feynman diagrams at work, so let me just quickly go through these cartoons. There's one photon exchange. We can have more sophisticated exchange. This is what we call a vertex correction. This is what we call a vacuum polarization correction. Let me stop and talk about this one. Here we have our two scattering electrons. One electron emits a photon, which disintegrates into electron-positron pair. The electron-positron pair ultimately get back together to create a second photon. It's the second photon that's responsible for the repulsion. So we add up hundreds and hundreds of these kinds of diagrams to calculate the anomalous the anomaly of the G-2, and we have better than 1 in a billion agreement. In fact, I like to point out to people that this is staggering. There's no other piece of science where you have a theory where you can, on the one hand, that you can compare experiment, and you have better than 1 in a billion match. So relativistic quantum field theory is, in fact, the most accurate theory humans have ever created. The standard model is the most accurate piece of science that has ever been created. So let's go to the standard model. As you probably know, one of the weird effects of quantum mechanics is that coupling constants, the value of coupling constants appear to change with energy. The analogy that I can give you is that if you have a pool in your yard and you float in your pool, if someone begins to put dissolved salt in the pool water, you'll find that you'll float and fly higher and higher levels. That's true. Well, energy works like that when you try to measure the strength of something like the coupling on an electron. It actually changes with energy. This is an effect that was discovered in the 70s, Weinberg and I can see her face, but I can't think of her name. Quinn and Weinberg were among the first people to understand this relationship between the strength of a coupling constant and the energy at which you measure. And what happens is you find this. So let me explain this picture. In the first picture, what I've shown are the coupling constants for the strong interaction, the electromagnetic interaction, the weak interaction, and gravity. Those are numbers that you can go measure. They're in our table of physical constants. But if you measure these things in the context of a quantum field theory at different energies, these numbers change. It's kind of like the effect of shielding that it goes on when you have a charged particle in a gas of charged particles. If the gas has the opposite sign to the particle put in, you get an agglomeration of the opposite charged particles, and then effectively it means that the particle you're looking at looks like it has less charge than it actually has. It's that effect that goes on with the coupling constants. And so if you measure the coupling constants, as Weinberg and Quinn found out, they run. This is called the process of running the coupling constants. And it looks like this. It tells a very interesting story. It says that the strong coupling constant actually gets weaker at higher energies. It says that the electromagnetic coupling constant also gets weaker for a while, and that the weak interactions become stronger and gravity becomes stronger. So that, in fact, the electromagnetic coupling constant and the weak coupling constant become the same value of what we call the electroweak transition. If you go to even higher energies, you'll find out that the strong coupling constant changes and also assumes the same value. And then finally, at some incredibly high energy, very close to the Planck energy, you find out that all the forces have the same magnitude. And this picture, which is a picture in energy, can also be thought about as a picture of how the universe evolves. Because at its Big Bang, we believe all the force carriers did have the same energy. And then as the universe begins to cool and expand, the force of gravity breaks out first. It becomes the weakest of the forces. It continues to cool and expand. This here is the stage where when the strong coupling constant diverges, is when you can now begin to form atomic nuclei. And then finally, as you watch the divergence here, you can actually begin to form the first hydrogen. So this is also a story about the evolution of our universe, not just about the coupling constants. So, Susie says something different. This is what we know from our observations. This is what supersymmetry predicts. That in fact there's a single point of joining for the standard model forces, a different kind of unification pattern. Which means that if our technology was really good enough, we might be able to detect the difference in these trajectories of the running of the coupling constant to give us an indication of supersymmetry. But our technology is not up to that. Another thing, probably from cosmology, you've seen this chart. That is, all the physics we ever have studied is about 5% of the stuff that we think exists in the universe. This is dark matter stuff, which we're going to come to shortly, and there's dark energy. Dark matter goes back to Fritz Zwicky and another name that I'm blanking on, back in the 1930s. Vera Rubin and colleagues in the 1960s observed the same effect, that when you look at rotation rates of stars at the edges of galaxies for other galaxies, you find out that they're rotating too fast compared to the amount of matter you can account for. And so we think there's other matter that you can't see. That's the so-called dark matter. And so let me concentrate on dark matter for a bit. Dark matter also turns out, and this is a little cartoon I created, also turns out the lifetime of galaxies is also very much related to the presence of dark matter. Here we have in this cartoon image, we have some simulations where in the upper percent, I just sort of salt around a bunch of stars, set it in motion, and watch what happens. You begin to see something that looks close. Something like a pinwheel appears, something like our galaxy with its pinwheel arms, but the time scales are such that this thing, in fact, begins to fall apart. Whereas the presence of dark matter actually delays this process. So when you start comparing lifetimes of galaxies, that's another reason why you want to have dark matter. There's a more stunning reason called baryon acoustic oscillations, which have to do with the formation of galaxies themselves, that also the cosmologists will now tell us crucially depend on the presence of dark matter. So we're pretty sure dark matter's there. Our Higgs boson, about 125 TeV. But this means that we live in a very funny universe. In fact, there's a property called naturalness. If you flipped a bunch of coins, this is the unnatural state. You expect heads or tails, but you don't expect it to land stay on its edge. Yes, sir.
I flipped a coin once and it did land on its edge.
I'm sorry, what'd you say?
The probability is 1 in
It did land on
6,000.
its edge.
The probability is 1 in 6,000. I read somewhere.
Well,
In a quantum mechanical universe, it's probability we have to worry about, right?
yeah, it was rolling and it came to rest against the base of the land on its edge, and it did not.
Okay, well,
There's explanations for these things, but it did happen. I didn't expect it to land on its edge.
well, it turns out that there's a sense in which we live in a universe that apparently is on its edge. And that's the problem, is why. And that's the problem that particle physics call naturalness. So if you come across discussions of naturalness, this is the issue that's being discussed. Namely, that, so the story goes as follows. I have told you we've discovered the Higgs boson, and apparently we have. I've told you this is in the context of quantum relativistic field theory, because that's the mathematics that gives us the confidence that at 1 part in a billion we got the right answer. When you combine these two things and look at the mass of the Higgs particle, a puzzle emerges. And that puzzle happens that when you, in the context of relativistic quantum field theory, if you try to understand the mass of any spin zero particle, when you add in the quantum effects of that, it's unlike any of the other kind of particles we've ever seen. In fact, you get these huge corrections from quantum mechanics, and so you have to do a process we call fine-tuning. Namely, at each ordering corrections, you have to add on, in a very arbitrary fashion, you have to add on something to the effective Lagrangian that cancels these quantum fluctuations. This is the naturalness problem. And so, if you find a Higgs particle like 125 TeV Higgs particle, I'm sorry, TeV Higgs particle, GeV, you have to wonder why the quantum fluctuations allow it to be so light. That's the naturalness problem. And that's what this quarter represents in non-technical terms. And this is something people in my field have been wondering about for about 30, 35 years. Why do we live in such a universe?
Let's go back for a moment to why it is so light. Because 126 sounds like a large amount of
Well, I
energy
mean-
to me.
It's comparable to the W and G.
Yeah, well, it's like when my community talks about light, we're talking about light compared to, how do I say this? If you believe in perturbative relativistic quantum field theory, that mathematical context breaks down at around 600 or so GeV. At that point, you no longer have confidence in the perturbation expansion. So in comparison to that number, 125 is considered light. So that's why people say it's a light
20%. So
20%. If it seems like I'm having fun, I am.
Well,
So, as I said, back in 2006, I talked about the fact that I did not expect supersymmetry to be found. It's in this article that was published by an organization that I think we all know and love here, the American Institute of Physics. And in this, I talked about my expectations. And I said it was more likely that supersymmetry will emerge by indirect means. So I'm going to sort of end by going there. If you look back at the Higgs particle discovery back when it was first announced, there was this plot. Oh, so what are we looking at here? So the Higgs particle decays. It's not a stable particle, but it has lots and lots of decay modes. So here's the decay mode of the Higgs particle going to bottom quarks. Here's the decay mode of the Higgs particle going to tau leptons. Here's Higgs to 2 gamma, Higgs to 2 Ws, Higgs to 2 Zs. And what you're looking at, what these red lines represent, are the width of those decay modes as measured at the LHC. The green lines here, and of course, the measurement is the central dot. The red lines around it are the values of the uncertainty, because good science, we always know there's uncertainty. The green, the solid black line here is the prediction of the standard model, but you also have to account for the fact that you have uncertainties there too. So that's the width of this green line.
Prediction from the standard model?
Yes, because the standard model predicts the width of the decay modes.
The width.
So, so this is what the situation was like in 2013. And if you look at this, there's something really funny. Here is this decay mode of the Higgs particle going to 2 gamma. Here's the uncertainty in that. And you'll notice that the uncertainty is outside the width of the uncertainty in the standard model. And it was this that was the cause of that funny language in the announcement that came out of the LAC. Because if this piece of data had held up, then there's something funny. You say you found a Higgs, but you can't explain all of its decay modes.
Is that a 1 sigma uncertainty?
I think it was about I think it was almost 2 if I remember correctly.
The bar is 2 sigma?
I think that's about 2 sigma.
Because if it was 1 sigma, it wouldn't be significant at all.
Right, exactly. And that's what I think it was about 2 sigma. I think it was about 2.
1.5.
Well, 1.5, yeah, something like that.
Like,
So that's what all that funny business was in the initial announcement, because they were very much aware that one of the decay modes was not lining up. Now the reason we're no longer uncomfortable with this is because in the subsequent scientific runs, where you have about 8 times as much scientific data, what has happened is that this decay mode central value has shifted in this direction, and the error bars have decreased, so that now we're comfortable saying that, yeah, the Higgs particle, today if you talk to any of the particle experiments on Higgs boson, they'll say, yeah, we have found the Higgs boson on the standard model, because we can actually line up these decay modes also. So, I pointed out to you folks that there's this experiment called LHCb, which doesn't get very much notice. But LHCb, and in fact, even at the Stanford Linear Accelerator, people have been watching and measuring decay modes for the heaviest quarks, the top and bottom quarks. And there were hints back in the old days at the Stanford Linear Collider that they were not seeing the numbers they expected. In this diagram, this is the standard model prediction over here. These are the kinds of measurements that are being seen at LHC for the decay rates of the top and bottom quarks, and I can't remember what they're decaying into, but the point is it's here. And as you can see, there's this divergence. It's about a 2 sigma effect, someone had asked earlier. This is about 2 sigma effect here. And so there's something funny going on that nobody knows how to explain these results that are coming out of LHCb. And there have been other hints. This is another paper that I pulled from the archive around 2015, where they're looking at decay modes of the B quarks. And again, there seems to be something funny going on. One more paper. So this is a persistence, low-level discussion in the community among the experts who are studying it. It hasn't gone away, and it has persisted now for over 5 years. So if these anomalies and branching ratios begin to grow with further analysis, then in fact we will be in the post-Higgs era, because there's nothing in the standard model that can explain this. And this was the way I thought we would see the first signs of supersymmetry. Not by direct detection, but by branching ratios, decay modes, and what have you. And that's what I wrote in my 2006 Physics Today articles, that that's the way to think about looking for these things. I have to tell you that my technical reason for doing this is that when you look at the electric dipole moment, the G-2 experiment basically, and you look at the Feynman diagrams that contribute to it, the value of the G-2, which we measure, depends on the masses of the superpartners that you put in those Feynman diagrams. And so in order for that agreement to what we know experimentally compared to the masses of the proposed superpartners, it turns out that predicts that you should think about super partner masses around 30 TeV, not the numbers that we can see now in the galaxy. And that's what's in my 2006 article on Physics Today. I thought that ranges like 30, 60 TeV. That's, if superpartners are there, that's where I would expect it. But of course, like Cassandra having made predictions doesn't mean people listen to you.
Well, until afterwards.
Until afterwards,
And we're
exactly.
not gonna see any 30 T.
And we can't. That's exactly right. If my intuition is right, we're not going to see them in this second scientific run either. And so that's why I said attention should be looking at indirect detection. Yes, sir.
Yeah, and there's an old Arab saying that he who predicts the future lies even when he's telling the truth.
Absolutely, and that's certainly true.
Uh-huh.
So even in the face of this daunting experimental challenge, why do I believe in supersymmetry? Well, it goes back to something really why I started studying. There's a problem called a false vacuum problem, which is illustrated by this diagram. Namely, if this is an energy surface, and you have some, say, quantum system, if the system is prepared in this state, it can stay there actually pretty long time. But because of tunneling in quantum mechanics, we know that ultimately it will go to the true ground state system. So this is what's called a false vacuum. It's a well-described, well-understood quantum mechanical effect. So when I drew that picture of the Higgs boson potential for you, I drew it so that it came down like this, then it went up, but does it go back down? See, we don't know the answer to that question. And if the Higgs boson is actually caught in a false vacuum, then there's a quantum mechanical possibility that it will decay into the true vacuum. But if that were to occur, the Higgs particle would lose its mass, everything would lose its mass, and the universe would collapse.
Uh-oh.
A big oops.
Why would it collapse without any mass?
Because if no particles have mass, then all particles must travel at the speed of light. How do you get balance states? Right? You're going to collapse the universe.
Thank you.
You're welcome. I'm glad you think that's a great thing. A lot of us are highly disturbed by this concept. So if our universe is really like this, then we're good. But if we're over here, then one has to start to worry. And in fact, it was observed that the ratio of the top quark to the mass of the Higgs particle began to suggest that maybe we are in a false vacuum. There have been some mathematical studies done of this. As I said, this is a paper that was actually published, I think, 3 years ago on the subject, and it's not the only one. And so here's our 125 GeV Higgs. Here's the mass of the top quark. We're really in this metastable region of the clock.
Right on the edge.
Right on the, I'm sorry?
What's the time scale for tunneling?
Oh,
As
God.
opposed to, say, the sun blowing up or something?
Yeah.
Longer.
It's longer than the time. Well, first of all, we know the sun. When you say blow up, I assume you mean the red giant stage of the sun, because it's not going to blow up in that sense. That's 5 billion years. I don't recall the time, but I suspect it's considerably longer than that. But the problem is, as you know, just because you have the lifetime doesn't mean it can't happen tomorrow. Right? It's a quantum mechanical universe.
Yeah. That's the average.
Yeah, right. That's the average.
And
So
how do
we live
know-
in this. I'm
How
sorry.
do we know that somebody in some other alternate reality isn't going to do some experiment that makes our universe collapse?
So
How you communicate.
I'm extraordinarily conservative on the idea of the multiverse, which is a very popular and widely discussed idea. The word multiverse has a couple of different definitions. The one that aligns with your comments is one that I don't know how to take seriously as science.
If the tunneling decay, would all the Higgs tunnel at once? Isn't that something that you don't lose one or two?
The problem is that how do I say it? We're talking about the Higgs field. We're not talking about individual Higgs particles. We're talking about the field itself. And if the field loses its vacuum value, then we're dead meat. That's the issue. So we live in this quantum mechanical universe. It may be metastable. So that means it's like this. And if we live in a universe like this, where you can think of the quantum fluctuations as being little taps being applied here, you'd probably like to live in a universe where the number of taps from this side is balanced by the number of taps from that side. Because even though the universe is metastable, if the fluctuations on it basically even out, it will continue to exist in this metastable state. Now it turns out, first of all, thank you, that supersymmetry is the only mathematical construction we've ever seen in relativistic quantum field theory where that balancing of taps actually occurs. The simplest way to see this is if you have had a course in relativistic quantum field theory, one of the exercises that people give you is to quantize the massive but non-interacting Klein-Gordon field equations. This is a process that you can do using what's called canonical quantization. And it's an exercise we give our graduate students in graduate school, and you ask them to calculate the Hamiltonian associated with the system. And if they properly do the calculations, they'll find out that that Hamiltonian has an infinite constant associated to it. The traditional and conventional thing that we have done at that stage, we tell our students, we all know that when a constant is added to a Lagrangian and Hamiltonian, it doesn't affect the dynamics. So just ignore that constant, right? And that's what we've told our students for decades.
Renormalization.
Renormalization, exactly. Now, it turns out that if you start with a supersymmetrical theory, so you have to have particle and boson, and ask that same student to do the canonical quantization and calculate the Hamiltonian, it turns out that the infinite constant you get from the boson is exactly cancelled by the infinite constants you get from the fermion, and so to get taken together, they're zero. And that's the thing that first fascinated me about supersymmetry when I was a graduate student, because it removes this arbitrary step of saying, there's an infinite constant, let's just remove it. Now, there are other reasons for renormalization besides this one, but this one occurs before you do any interactions, and that's why it's different from the other ones. So this is a very primitive kind of renormalization, and supersymmetry is the only class of theories that we have seen that has this property to damp out quantum fluctuations. And like I said, if I live in a universe like that, I sure want a lot of damping. Thank you. Now,
Question.
yes, sir.
I mean, on the standard field theory calculation for the cosmological constant.
Oh, God.
You get you this number, it's 10 to 120 times.
Yeah.
And the experimental value is very small, about
Yes.
0.
Yes.
And is it possible that there is, again, some sort of a sort of a cancellation that cancels out the first order, but
Jack,
leaves us?
that's an extraordinarily interesting observation, because as long as our observational data supported zero cosmological constant, it could then be argued that the absence of the cosmological constant was related to this cancellation of quantum fluctuations that you see in supersymmetrical theories. But as you said, observationally we know there is a small value. So you could maybe argue that the fact that it's so small may still be some kind of indication that supersymmetry.
It cancels
Up
to
to
high order, but there is a small.
some kind of residual.
Yeah.
Yes, sir.
Next month's presentation is laboratory effort there, at the University of Louisville for a particle to associate with dark matter.
Yes.
Is it conceivable that it's not a particle, that it's some continuous thing?
Well, you have to understand. When people like me use the word particle, we're using an interchangeable field. That's right. They're not distinct in the way we look at physics. So when someone talks about a dark matter particle, they're talking about a dark matter wave function. So it's not just a particle. And that, oh, by the way, I'm sorry.